Hey everybody, let's look at this one from 2002 here. We've got a 2 kilogram frictionless cart. It's going at a speed of 3 meters per second to the right on a horizontal surface. It collides with this second cart, undetermined mass m, that's initially at rest. That's probably going to be important there, as is this 3 meters per second, as is this 2 kilograms there. The force F in the collision as a function of time t is shown in the graph below. So as a result of the collision, the second cart acquires a speed of 1.6 meters per second to the right. Assume friction is negligible. All right, we will. So they give us this force versus time graph. So right away, when you see force versus time, then you should be thinking impulse. And then you should be thinking also potentially change in momentum, because those two things are equal to each other there. And then the way we get that from this graph, remember, is the area. Since impulse is force times time, then anything where we're doing force times time will get us the impulse there. So since this is a triangle here, we're going to do 1/2 base times height here for the triangle. In this case, we'll get 1/2. The base is 1. Now, maybe you missed this. It's 1 millisecond there. And then the height here, it goes up to 10, but in case you miss it, it's 10 kilonewtons there. It's kind of funny that they did those two things, because if you just missed one of them but caught the other, you'd get the wrong answer. But if you miss both of them, the kilo cancels out with the milli, and it's like that neither one was even there. So 10 times 1 basically times 1/2, that winds up being 5 kilogram meters per second, or 5 Newton seconds if you wanted that to report it that way, of impulse or change in momentum. All right, so what we're ultimately going to do here is calculate the magnitude and direction of the velocity of the 2 kilogram cart after the collision here. So let me scoot this up just a little bit. If we already know the change in momentum is also equal to mass times change in velocity. So we know the change in momentum, we know the mass, so we can solve for the change in velocity fairly easily there. All right, change in momentum is 5 kilogram meters per second, and we set that equal to the mass of 2 kilograms and solve for the change in velocity. So we will get a change in velocity of 5 divided by 2 of 2.5 meters per second. Now, careful. That is not our answer. Our answer is not 2.5 meters per second. That's how much it changed by. Then, in addition to that, you need to think about this. Since this cart here is coming along, it's going to get pushed backwards, right? So the 2 kilogram cart's going to slam into this one, so it's going to be pushed backwards. So this impulse is going to slow it down. It's going to take away 2.5 meters per second of speed. So we had 3 meters per second of speed. We take away 2.5. That means our final speed is 0.5 meters per second there. Okay, let's move on to part B here. They say calculate the mass of the second cart. Well, actually, let me bring this back up for 1 second. Due to Newton's third law, not only is this the force of cart M on cart 2 kilograms, but it's also the force of cart 2 kilograms on cart M. Has to be according to the third law. So the third law dictates that we already know the impulse or the change in momentum of this cart, and it is also 5 Newton seconds or kilogram meters per second, whatever you want to call it there. So since that's the impulse, that's the change in momentum, that is mass times change in velocity. So we're looking for the mass, and we actually already have its change in velocity, so we can plug that in there. So 5 kilogram meters per second is equal to, we're trying to find our mass, and our change in velocity is, they said it went from 0 up to 1.6. So our change in velocity is 1.6 meters per second. So then we just take 5 divided by 1.6 to solve for our mass, and we get 3.125 kilograms there. All right, so next part here. Now, that was all this unit, which is momentum and impulse. Now the rest of this is kind of review. So they say after the collision, the second cart eventually experiences a ramp, which it traverses with no frictional losses. So the graph below shows it going up that ramp. So it had some speed until it hit the ramp, and then it slowed down. Then it must have gotten to the top of the ramp there. So the first thing is they say calculate the acceleration of the cart. So all they're looking for you to realize is that acceleration on a cart like this, or on a graph like this of speed versus time, the acceleration would be the slope. And so we're going to find the change in velocity over the change in time there. Right here, remember change is going to be final minus initial. So we wound up at 0.5 meters per second, but we began at 1.6 meters per second. And make sure you can see that dot there. And then the time is that occurred from 2 to 3.5 seconds. So that took 1.5 seconds to happen. So if you do 0.5 minus 1.6 divided by 1.5, you'll get negative 0.73 meters per second squared. So good review from the first kinematic unit there of how to get the acceleration from a speed versus time graph. All right, next one up here. It says calculate the distance traveled by the cart during the 5-second interval during the collision. There's multiple ways that you can do this. You can bust out some of your kinematics. The only thing about doing it with kinematics is you got to realize that you'll have different equations for each part, but that's totally fine. This section's accelerated. These two sections are different constant speeds. So you can use some kinematic equations there. I'm just going to do this. The distance traveled on a graph like this is the area. So remember, another good review, that the area under a speed versus time graph is the displacement. So what I'm going to do is actually, since this is a weird shape, I'm going to create a box right here. That's going to be one of my areas. This box is 5 by 0.5. So this box here, 5 by 0.5, gives us here 2.5. And then let's see here. We've got another box right here. This box is 2 by, here we start at the 0.5 and we go up 1.1. So this box right here is 2 by 1.1, so it's 2.2 meters. And then finally, our last one here, we've got a little triangle right here. And so that little triangle there, let's do 1/2 base times height. Our base is 1.5. And our height here goes again from 0.5 to 1.6. So our height is 1.1. And actually, let's see here. I forgot my calculator on this one. Let me grab that real fast to figure out what this is. So 1.5 times 1.1 times 0.5 is 0.825. And so those are our three areas here, 0.825, 2.5, and 2.2. So we can add all of those up. We get 5.5 basically, 25, so it keeps going there. So 5.25, or excuse me, 5.5, let me restart here, 5.525 meters. All right. So finally, it says state whether the ramp goes up or down and calculate the maximum elevation reached. So you may get here and be like, what the heck? This is also a review. This is conservation of energy. I'm actually going to utilize some of the space up here for this one so we have a little bit more room to work with. So if it goes up the ramp, we know that we have kinetic energy that is going to become gravitational potential energy here. So if I think about it this way, and by the way, both of these are a change. So we're going to have some drop in kinetic energy and some gain in gravitational potential energy. So if I write this here, we can have our kinetic energy final here minus our kinetic energy initial is going to be equal to our gravitational potential energy final minus our initial. But we might as well call where we began 0. So, and we'll just think about how much we climbed there. And that way we only have to deal with one gravitational potential energy there. So now let's start to plug in for these here. So my final kinetic energy will be 1/2 times mass times final velocity squared minus my initial kinetic energy, which will be 1/2 times times mass times initial velocity squared, and that will be equal to mass times gravity times the change in our height. Notice the mass does not even matter, even though we have solved for it. We don't need it. So now on this side here, be careful because there's a chance for a little algebra mistake here. I'm going to write it like this. I'm going to factor out the 1/2, and we get v final squared minus v initial squared. Don't do v final minus v initial and then square that. You will not get the same answer in that case there. And that is going to be equal to gravity times our height there, which is what we're looking for. So now we're just about ready. We can start plugging in here and solving. So 1/2 here times our final velocity. We got to get that off of our graph, right? We went all the way down to 0.5 meters per second. So 0.5 meters per second squared minus our initial velocity, which if you look on the graph was 1.6 meters per second squared. And then that is going to equal gravity, which is 10, times this height that we are looking for. And then when we solve for that height, we're going to get 0.1155 meters is our change in height.